Hello everyone. What I'd like to do in this video is show you a technique for building polynomials. Okay, so let's say our boss gives us a project and our job is to build a degree 3 polynomial. It has specific roots and I know a little bit of knowledge, or I want one of the terms to have a specific coefficient. I want the x squared term to have a coefficient of 2. So go ahead and pause the video and see if you can do this problem on your own. Okay, so let's see what we must know about this polynomial. The first thing to know about this polynomial is we know knowledge of its roots. So we know that 5 is a root, 0 is a root, and -1 is a root. So what must this mean? This means I know information about the factored form of the polynomial. So let's try to start building it. Well, if x equals 5 is a root, that must mean that this polynomial in its factored form must have an x minus 5 in it. Similarly, if I know that this polynomial has 0 as a root, then I know, I guess, that x minus 0 must be one of its factors. But instead of writing x minus 0, how about we just put an x out front? So we're trying to build a polynomial that has these specific roots. Similarly, if x equals -1 is a root of this polynomial, I know that this polynomial must have x plus 1 as a factor. Okay, so this polynomial right now, I think I've met two of these three conditions. One, this polynomial has 0 as a root, 5 as a root, and -1 as a root. Also notice that this polynomial is of degree 3. If we multiply those all together, or like we did in 3.2, we can tell what degree this polynomial is by adding the exponents. 1 plus 1 plus 1, 3. It's a third degree polynomial, has those roots. Now the only thing I need to make sure of is that it has a coefficient of 2 on the x squared term. So before I go on, I just want to make a comment here. That basically what I'd like to say is there are actually an infinite number of polynomials that have these as roots. For example, here's a polynomial that has these roots. But what if I just put a 2 out front, like I multiplied this polynomial by 2? Now think about what this does here when I multiply the outside of a function by a 2. Remember, this stretches the graph. So let me kind of just draw a picture of this. So right now this polynomial has a root at 0, it has a root at -1, and it has a root over here at 5. Okay, maybe we could think about what this would look like. Okay, what would be its end behavior? It's a third degree polynomial, so it would look like this. Its end behavior would be like an x cubed. There's no negative out front. Or imagine that I don't have any other coefficients here. I guess this coefficient is positive, and I'd have this behavior here. Now each of these have a multiplicity of 1, so this polynomial as of right now would just look like this. But now if I took this polynomial that has these roots and I multiplied it by 2, if I multiply it by 2, all that's going to do is that's going to stretch all my outputs. It's still going to have 0 as a root, it's still going to have 5 as a root, and it's still going to have -1 as a root. It's just this graph is now just going to be stretched out. Or maybe instead I multiplied the number out front, but I don't know, how about like I don't know, by -3. So it's still going to have these roots, but now it's going to reflect the graph and stretch it. So now the graph is going to be way more stretched, and it's going to be flipped. So what I'm trying to say here is if a polynomial, if it already have its roots, just by scaling this function does not change where the roots are. All it will do is stretch the graph or possibly reflect it, but it keeps the roots intact. Now we want to use that knowledge to help us figure out how to make sure that the coefficient in front of an x squared is 2. So what am I going to do? What am I going to do to figure this out? Well, what I'm going to do is I'm actually going to completely expand this. An unfortunate exercise, but I'm going to FOIL this out. I'm going to try to figure out what coefficient is on x squared, and then I'm going to scale the polynomial appropriately to make sure that the coefficient in front of x squared is a 2. So let's do it. So let's go ahead and FOIL this out. So we're going to FOIL. Okay, so the first thing I'm going to do, maybe I'll do it in red, is let's distribute in this x. So I'll be left with a x squared minus a 5x times a x plus 1. Okay. Now I'll FOIL this out. I'll get an x squared times an x. I'm going to get an x cubed. I'm going to get an x squared times a 1. I'll get plus an x squared. I'll get a negative 5x times an x. I'm going to get a negative 5x squared. And I'm going to get a negative 5x times a 1. I'm going to get a negative 5x. Okay. Okay, so now what we'll do here is we'll go ahead and add like terms. So here we have an x cubed, x squared minus 5x squared. What are we going to get? We're going to get a negative 4x squared minus 5x. Okay, note that the x squared term, its coefficient is a negative 4. That's not what our boss wants. What our boss wants is that coefficient to be a 2. So what I'm going to do here is I'm going to scale this polynomial by a number to turn this negative 4 into a negative 2. Or negative 4 into a positive 2. So what should I multiply this by? I should multiply it by a negative 1/2 because that'll turn this negative 4 into a 2. And we're finished. This is the polynomial. You could leave it like this. You could distribute in the negative 1/2. Sure, why not? But now we could go tell our boss that negative 1/2 times x cubed plus a 2x squared plus a 5/2 x. We say, hey boss, this is the polynomial you asked for. I want a raise. And that's how we construct this polynomial. Okay, let's do one more. Same idea. Let's build a polynomial. Okay. We'll just write down some of the conditions. What are the conditions I want for this polynomial? First condition, let's say it's a degree 3. Degree 3 polynomial. Second condition, I want 3, 1, and negative 2 to be the roots of this polynomial. Okay, and 3, I want a constant term of negative 18. Go ahead and pause the video and try this out on your own. Okay. So what do we know about this polynomial? We know information about its roots. So if 3 is a root of this polynomial, that means that x minus 3 must be a factor. If 1 is a root of this polynomial, that means that x minus 1 must be a factor of this polynomial. If x equals negative 2 is a root, then x plus 2 is a root of this polynomial. So notice here I've met 2 of the conditions. It has these as roots, and it's a degree 3 polynomial, 1, 2, 3. We just count the exponents, 1, 2, 3. Okay, now I need to make sure that the constant term of this polynomial is negative 18. Now I'll go ahead and FOIL this out for you in this situation, and then at the very end I'll actually show you a way you could have done this problem actually a little bit quicker. Okay. How can we brute force this problem? Just I guess how it's written is let's just start expanding. So let's expand this first. Let's FOIL it out. I'm going to get what? An x squared. I'll get an x squared. I'll get a minus x. I'll get a minus 3x. And I'll get a plus a 3 times the x plus 2. So it looks like we have an x squared minus 4x plus 3 times an x plus 2. Okay. Now if I want to expand this, I'm just going to multiply every term by every term. So I'll get, what am I going to get? I'm going to get an x times an x squared, an x times an x squared. I'm going to get an x cubed. I'll get an x cubed. I'll get an x times a negative 4. I'm going to get a negative 4x squared. I'll get an x times a 3. I'll get plus a 3x. Okay. plus, I'll multiply the 2 in. I'm going to get plus a 2x squared plus a negative 8, a negative 8x plus 6. If we combine like terms, what are we going to get? Hopefully we can still see this. Beautiful. Sorry, my handwriting's getting a little slanted. X cubed. Okay, well, how many x squared terms do we have? Negative 4. I have negative 4. I add 2. I got negative 2x squared. Took care of those. 3x, take away 8. What do I get? A negative 5x plus a 6. Okay. Unfortunately, we do not have a constant term of negative 18. We have a constant term of 6. So if I just scale this polynomial correctly, I'm not going to change the roots. All I'll do is I'll just change the constant term. So what do I need to multiply 6 by to get negative 18? Well, I think negative 3. And we're finished. So if we want to leave our answer in an expanded form, I can distribute in that negative 3. So what would we get? I'll write it right here. We'll get it right. I'll write a negative 3x cubed plus a 6x squared. What? Plus a 15x minus 18. And there we go. We did it, boss. We did it, boss. We need a raise. We need a raise. Okay, now let's talk about efficiency. Now, just for this specific example, how could I have shortcutted my work here? I didn't actually need to do all this ugly expanding. If I would have noticed, how did I get my constant term of 6? Well, notice that the constant terms, if it's a constant term, it's not going to get multiplied by a variable. So a shortcut is I could have just done the negative 3 times the negative 1. That gives me a positive 3. A positive 3 times a 2 is a 6. So I can already tell right off the bat that 6 is going to be the constant term just by multiplying these together. So since I know that the constant term is a 6, what would I need to multiply it by to get a negative 18? Multiply it by a negative 3. And maybe now your boss is even more impressed. Your boss is even more impressed because you took up less time, you're super efficient, and you have the polynomial nicely factored for him. It's beautiful. So I would accept either one of these for full credit. Whether you presented your boss's polynomial in an expanded form or in a factored form, both would be correct. Hope you enjoyed this video. In the next section, we're finally going to figure out how are we going to find possibilities for roots of polynomials? Can we find candidates for roots so we can start using synthetic division to break down polynomials and factor them so then we can start graphing them? Okay, see you then. Take care.